Hello friends, in this video we will study about the block diagram of 8279 Programmable Keyboard Display Controller. So let's start with our topic. So this programmable keyboard display controller, its IC name is 8279. This is used to interface the keyboard and the display devices with the central processing unit or the microprocessor based systems. So we can say that it is, we can write here the use of this 8279 used to interface. It is known as a path which is providing the communication link between two components. Okay, so we can say that interface here, this keyboard display controller 8279, it is acting as an interface between the keyboard and display devices and the central processing unit or the microprocessor. So now let's come to the block diagram of this 8279. Let us study the different blocks in this 8279. So let us come to the block diagram of this 8279 Programmable Keyboard Display Controller. This is the block diagram of 8279. This block diagram, it consists of 4 sections. One is the keyboard section, one is the scan section, display section and CPU interfacing section. So in this block diagram, you can see that there are various blocks like data buffers. This data buffer is connected with the data bus DB0 to DB7. Then we have the internal data bus of 8 bits. Then we have control and timing registers, timing and control unit. We have 16 into 8 display RAM and also we have 8 into 8 FIO Sensor RAM. Now we have the display register, display address registers. This is scan counter, return, keyboard debounce and control block. Then we have FIO Sensor RAM status and input output control. We have various signals also like clock, reset, read, write, chip select, A0, interrupt request signal. Then we have BD, that is blank display, out A0 to A3 and out B0 to B3. Also we have the scan lines SL0 to SL3 and we have the return lines RL0 to RL7. Then we have shift and control strobe lines also. So let us study these blocks one by one. First, we will divide these complete block diagram into 4 sections like the keyboard section, scan section, display and CPU interfacing section. So we can say that the 4 sections are, first is keyboard, second is a scan, third is display, and fourth is CPU interface. So in the block diagram, if we see this keyboard debounce and control, return and FIO Sensor RAM status, this forms the keyboard section. Then we have the FIO Sensor RAM and scan counter. This is the scan section. Here we have the display address registers and display RAM, display registers. So this is the display section. And then this is our CPU interface section. So let us study these four sections one by one. First, we will start with the keyboard section. So in the keyboard section, you can see we have the return lines, RL0 to RL7, shift, control, and keyboard debounce and control unit. So let us study about this section. This section consists of the 8 return lines RL0 to RL7. So these return lines RL0 to RL7, they can be used to form the columns of a keyboard matrix. You can see in the block diagram, we have the return block to which the 8 return lines RL0 to RL7, they are connected, and these lines are used to form the columns of the keyboard matrix. In the keyboard matrix, we will have the rows and columns. So columns are the return lines. Okay. Now it has the two input lines also, the shift and the control stroke, and these lines, they provide the status of the shift key and the control key, and these keys are automatically debounced. Two additional input lines, we can say, shift and control stroke. Now this keyboard section, if we discuss the modes of 8279, then there are two modes. One is the keyboard mode and second is the display mode. So in the keyboard mode, we have two types of mode: 2 key lockout and N key rollover modes. So if we talk about the modes of this keyboard section, we will have two modes: 2 key lockout and N key rollover. So in the 2 key lockout mode, when two keys are simultaneously pressed, then only the first key is recognized. Whereas in the N key rollover mode, if two keys or more than two keys are pressed, then each of the key will be recognized. So these are the two modes of the keyboard section. Okay, 2 key lockout and N key rollover. Now this keyboard section, it also has an 8x8 FIO sensor RAM. This RAM, it is used to store the key codes which are associated with the key which is pressed in the keyboard. Okay, so the key code of that pressed key will be stored in the FIFO RAM, and the size of this is 8x8. So we can say that this keyboard section, it has an 8x8 FIFO sensor RAM. This FIFO stands for first in, first out. Means we studied the two modes of storage, LIFO and FIFO. In the computers you will have studied, and FIFO stands for first in first out and LIFO stands for last in first out. So first in first out says that the element which is first stored in the memory, that will be the first which is output from the memory, which will get out of the memory. Okay, so this RAM, it works on the first in first out basis. Now in the FIFO RAM, the key codes are stored. The key which is pressed, the key code associated with that pressed key will be stored in the FIFO RAM. So as per the sequence in which the keys are pressed, in that sequence only the key code of every pressed key will be stored in the FIFO RAM. Okay. Now this FIFO, it can store, because its size is 8 cross 8. So it can store 8 key codes at a time. And these 8 key codes, the key codes along with the status of the shift and the control key, they are stored in the, they are also stored in the FIFO RAM. Okay. So the 8 key codes, or the key code along with the status of the control and the shift key, they are simultaneously stored in the FIFO RAM. So if we see the format of this 8-bit keyword, it will be like, so this D7 bit, it is the status of the control key. D6, it is the status of the shift key. D6 status of shift key. D5, D4 and D3, these are the binary value of the row in which the key is closed. Okay, because we want to send the information to the CPU that because the keyboard, it has 64 keys. Okay, and these 64 keys, they are placed in some rows and columns. So we want to give the information to the CPU that in this row and in this column the key is pressed. So D5, D4 and D3, it is the binary value of the row in which the key is pressed, and D2, D1 and D0, it is the binary value of the column in which the row is in which the key is pressed. So in this way, the CPU will get to know that it has to go in this row and in this column, and the key code of that row, or the information of that key, will be transferred to the CPU along with the status of the shift and the control key. So this whole information, it will be stored in the FIFO RAM. Okay. Now in this keyboard section, we have studied this return section also. Return has this return lines and the shift and control input. Then this RAM also we have studied. Now we are left with this keyboard debounce and control section, and also this FIFO sensor RAM status, it also comes under this keyboard section. So this FIFO sensor RAM status block, so this FIFO sensor RAM status block, it is going to, because whenever any key is pressed in the keyboard, then key code will be stored in the RAM, and because this information which is stored in RAM, it has to be read by the CPU. So CPU or the microprocessor, it has to be interrupted. Okay, so whenever key is pressed, then an interrupt signal will be sent to the processor or the CPU. So this FIFO sensor RAM status, whenever any key is pressed, then it is going to generate a request signal which is known as this interrupt request signal, and this signal will be sent to the CPU. Okay, and this through this signal, the CPU or the processor, it is going to be interrupted, and then the CPU is going to read the key code from this RAM. Okay, so FIFO sensor RAM status, it generates an interrupt signal when there is an entry in the FIFO RAM. Okay, now the format of the key code entry, we have already studied that it has these 8 bits. This is the format of the key code which is entered in the FIFO. Okay, now this was in the keyboard scan mode. Whenever the keyboard section, it is in the keyboard scan mode. Now when the keyboard section, it is in the scanned sensor matrix mode, so in place of keyboard, a sensor will be connected. So keyboard was having 64 keys. Now in the sensor array, we will have the 64 switches. Okay, so 64 switches will be connected to the 8279, or they will be connected to the CPU. So the information about the 64 switches of the sensor, they will be stored in the in this FIFO sensor RAM. Again, the status will be stored, and this status will be read by the CPU. Okay, so only the function is changed, that in keyboard mode, the keyboard, the information about the key which is pressed will be stored, and in the sensor matrix mode, the status of the 64 switches will be stored in the RAM. Okay, so here I can say that in the scan keyboard mode, these are the modes of 8279. So in the scan keyboard mode, the information about the 64 keys, that whether any key is pressed or not, that is stored in FIFO RAM. And in the scan sensor mode, the condition of 64 switches, that whether the switch is on or off, that will be stored in the FIFO RAM. And whenever this switches are on, means whenever any switch is on, then the interrupt request signal will be generated, and if any key is pressed, then also the interrupt request signal will be generated. So in the keyboard section, we have seen that what it consists of. It has this FIFO sensor RAM, it has the return block, it has FIFO sensor RAM status. Now we are left with this keyboard debounce and control unit. Okay, so what's the function of this unit? Whenever any this, it will get the input of the return lines, also the shift and control input will be given to this keyboard debounce and control block. So whenever any key is pressed, this is going to store the key code into the sensor RAM. Okay, so if we say here the function, then keyboard debounce and control unit, so this keyboard debounce and control unit, it first scans the key closure row wise, and if it finds that any key has been closed, then the unit debounces the key entry, and then it is going to transfer the key code into the FIFO RAM, and then Along with the status of the shift and control key, the key code will be transferred. So that is the function of this keyboard debounce and control unit. So this completes the keyboard section of the block diagram. Now let us come to the next section, which is the display section. Now the display section, it consists of, if we see the block diagram, then in the block diagram you can see that the display section, it consists of the display RAM, the display address registers and the display registers, and it has two lines of the group out A0 to A3 and out B0 to B3. So the 8 output lines, they are divided into two groups. Okay, so these 8 output lines, they can work as a group of 8 lines also and as two groups of 4 lines also. So this display section, it has 8 output lines divided into two groups. Out A0 to A3 and out B0 to B3. And these output lines can be used either as a single group of 8 lines also and as two groups of 4 lines also. Okay, and these output lines, they can be used in conjunction with the scan lines for a multiplexed display. Okay, now next in this we have the display address registers. Now these display address register, they hold the addresses of the word which is currently being read or written by the CPU to and from the display RAM. So whatever data which is currently being read or write by the CPU into this display RAM, the address of that data will be stored in this display address register. So these registers are basically used to hold the addresses of the data. Okay, now the display of the devices can be blank by the blank display line, which is an active low line. So its value, if it is 0, then the display will be blank. Here you can see that the timing and control unit, it has the signal BD bar, which is the blank display signal. Now this display section, it also consists of a 16 into 8 display RAM. The CPU, it can read from or write into any location of the display RAM, and this display RAM, it is of the size 16 into 8. You can see here we have the 16 into 8 display RAM and it is connected to the internal data bus and to the data buffers and data bus of the CPU. Okay, so through this data bus, the CPU can anytime it can read or write from this display RAM. Okay, so this was the display section in which we studied the display RAM, the display registers, display address lines, and the output lines. Now let us come to the scan section. So this was the display section. Now let us come to the scan section. The scan section, you can see here that the scan section, it has a scan counter in which it has the 4 scan lines SL0 to SL3. So here we can say that it has a scan counter and 4 scan lines SL0 to SL3. Now when the 8279, it is in the scan keyboard mode and scan sensor matrix mode. So there are 2 types of scan in it. One is the encoded scan and second is the decoded scan. So what is the difference between these two? In the decoded scan mode, the output of the scan lines will be similar to a 2 to 4 decoder, whereas in the encoded scan mode, the output of the scan lines will be a binary count, and so a external decoder will be needed to decode this code. Okay, so this is the difference between the decoded scan mode and the encoded scan mode. In decoded, we have the output of scan lines similar to a 2 to 4 decoder, whereas in the encoded scan line, the output will be a binary count. So the scan lines, they are used to form the row of a matrix keyboard and are also connected to digit drivers of a display to turn on and off the switches of the display. Okay, so this scan mode or scan section, it we can connect the keyboard and the display devices. Both can be connected, and both the keyboard and display, they can work in the decoded scan mode and the encoded scan mode. So when the keyboard is connected, then the scan lines, they are used to form the row of a matrix keyboard, and when display devices are connected, then they are connected to the digit drivers of a display to turn on and off these multiplexed display devices. So this was the scan section. You can see in the block diagram that scan section, it consists of the scan counter and the scan lines SL0 to SL3. Okay, now let us come to the CPU interface section, where we have the data buffers which is connected to the data bus. Then we have the input output control here. Okay, the CPU interface section, this unit, it takes care of the data transfer between the 8279 and the processor. So whatever data is to be transferred between the 8279 and processor, then the CPU interface section helps in it, because this section, it consists of the data bus and the data buffers. So through the data bus only the data is going to be transferred. So we can say that it takes care of the data transfer between the 8279 and the processor. It consists of the 8 bidirectional data lines, DB0 to DB7. These are the 8 bidirectional data lines, means bidirectional, so that the data can be transferred in both the direction, from 8279 to the processor and from the processor to the 8279. Now you can see in the CPU interface section that we have different signals here at the input output control. One is the read, write, CS bar, which is chip select, and this A0. Now this A0, it can be at logic 1 and at logic 0. So when the value of this A0 it is 0, then the data bus buffer will be selected, and when this A0 is equals to 1, then the control register will be selected. So it has two internal addresses, one for the data bus buffer and one for the control register. Now when A equals to 0, then data bus buffer is selected. It means that the data which is available on this data bus, it is the data which is to be written in either the display RAM or the FIO sensor RAM. Okay, means it contains the data. Okay, and when this A is equals to 1, then the control register is selected. So the data which is available on the data bus, it is a control word, and that control word is to be written into the control register. So when A equals to 0, data bus buffer will be selected and data is transferred, and when A equals to 1, then control register is selected and the data which is on the data bus, that control word will be written in the control register. Okay, so this line decides that which of the register will be selected. Then we have read for the read operation and write signal for the write operation. Okay, CS bar, it is for the chip select signal, means when this signal is low, then only this 8279 will work, this IC will be selected. So here we can write that we have the control signals. WR bar, which is the write, RD bar, which is read, and CS bar, which is chip select. And these control signals, they are used to read and write to the 8279. So whenever suppose this write signal is active and CS bar is active, then 8279, the data will be written into 8279. When read is active and chip select is active, then the data will be read from the 8279. So this is the function of the control signals. Now this CPU interface section, it also has one interrupt request signal. You can see here we have the IRQ here, which is generated by the FIO sensor RAM status. Okay, whenever key is pressed or whenever a display device is scanned or a switch is on, then this interrupt request signal is generated. So it has this interrupt request signal IRQ. for interrupt driven data transfer with the processor. Okay, so this interrupt request signal that will be generated by the 8279, and that signal will interrupt the processor, and then the processor is going to read the status or the key codes or status of the switches from the FIO sensor RAM. The 8279, this programmable keyboard display controller, it requires an internal clock frequency of 100 kilohertz. Now this internal clock frequency, how it is generated? This frequency can be obtained by dividing the input frequency by a prescaler. We have studied in the modes of 8279 that we have a programmable clock frequency mode in which the count is provided, the 5-digit count is provided, and the input frequency which is provided by the crystal, that is divided by that constant, that 5-bit constant, which is known as the prescaler, and that division will provide us the internal clock frequency. So this frequency is obtained by dividing the frequency, clock frequency, with the prescaler. Now in this we have the two signals also. Clock, we have studied the clock frequency, and then we have the reset signal. So this reset signal, it is used to reset or clear the contents of the control registers. So we can say here that reset signal sets the 8279. So the 8279, it has various modes. We have studied in our video of the modes of 8279 that there are various modes like keyboard modes and the display modes. In keyboard modes, we have also the 2-key lockout and the N-key rollover modes. So when the signal, the reset signal is set, means when its value is 1, then the 8279, this keyboard and display controller, it goes into the 16 character display with the 2-key lockout keyboard modes. So in the display mode, the 16 character display mode is selected, and in the keyboard mode, the 2-key lockout mode is selected. So this reset signal, it is going to set the 8279 in these two modes by default. Okay, otherwise if we want to change the mode of 8279, we can write the command word or control word accordingly, and then we will give this control word, write this control word in the control register, so that that program, that mode will be selected. Okay, so in the CPU interface section, you can see that we have studied the 8-bit bidirectional data bus. The data buffer is there, and in input-output control signals, we have the read, write, chip select, and the A0 signal, and interrupt request signal is also there, and clock and reset signal. Okay, so this completes the block diagram of the 8279. Then in this block diagram, we studied all the 4 sections: the keyboard section, the display section, scan section, and the CPU interface section. So I hope that this topic is clear to you. Thank you.